All right, let's dive right in. Today, we're going to talk about a fascinating corner of chemistry that is, believe it or not, everywhere. It's hiding in plain sight all around us. I'm talking about the invisible world of colloidal systems.
So, to kick things off, let me ask you something. What could fog, milk, and paint possibly have in common? I mean, really think about that for a second. They seem totally different, right? You've got weather, a drink, and, well, paint. What on earth is the connection?
Well, the answer is they're all colloids. Yep, one single scientific idea links all of these things, and a ton more you see every day. So that's the big question, right? What in the world is a colloid? Okay, so let's break it down. What makes a colloid? Well, a colloid. You see, it's this really special kind of mixture. It's not quite a solution, like salt that's fully dissolved in water, but it's also not a suspension, like sand that just sinks to the bottom of a glass of water. It's something else entirely. A colloid is basically a mix where these super, super tiny particles of one thing are just suspended throughout another thing. And that word, suspended, is everything. The particles don't dissolve, but they also don't sink. They literally just hang out in there. And every single colloid has two main parts. You've got the dispersed phase, that's the little particles floating around. Think of the tiny fat droplets in milk. And then there's the dispersion medium. That's the stuff they're floating in, which for milk is mostly water. So yeah, it's the stuff and the medium the stuff is in. Simple as that. Okay, but here's the real kicker, the secret sauce, if you will. The size of those particles is absolutely crucial. They have to be in this tiny, tiny window, somewhere between 1 and 200 nanometers. A nanometer is a billionth of a meter. It's almost impossibly small. And that specific size, that's what gives colloids all their cool, unique properties. So now that we know what they are, let's check out how many different kinds there are. And trust me, it's not just one or two. It's like a whole family tree of mixtures with 8 different types, and it all depends on what state of matter you're mixing with what. All right, have a look at this. This chart lays it all out. You can mix a liquid and a gas, a solid and a liquid, you name it. And each combo gets its own special name. For instance, if you get tiny liquid drops hanging out in a gas, you get what's called a liquid aerosol. That's literally what fog is. Or how about solid particles in a liquid? That's called a sol, which is what things like paint and ink are. This is where it gets crazy, because you see just how common these things are. Milk, that's an emulsion. Liquid fat and liquid water. We already talked about paint being a sol. Fog is that liquid aerosol. And whipped cream, come on, that's a foam. It's just gas bubbles trapped in a liquid. We are literally surrounded by this stuff all day, every day. But wait, there's more. It's not just about what they're made of. There's another whole layer to this. It's about how the two parts feel about each other. Seriously, do they like each other or do they hate each other? Chemists have a word for this, of course, affinity. And this affinity splits colloids into two big groups. On one side, you have lyophilic colloids. Think solvent-loving. The particles and the medium are best buds. They have a strong attraction, so they mix super easily and are really stable. Starch and water is a great example. Then you've got the total opposite, lyophobic or solvent-hating. Here, the particles and the medium want nothing to do with each other. They're unstable, and you often have to force them to mix, like when you create a gold sol. Okay, so this all leads to the biggest mystery, the million-dollar question. We know these particles aren't dissolved, and they're usually denser than what they're floating in. So why don't they just sink? What's defying gravity here? Right, so what is the secret? Well, it's not magic, it's just some really, really cool physics happening on an incredibly small scale. There are a few things going on, and the first one is something you've probably seen without even realizing it. It's called the Tyndall effect, and all it means is that the colloidal particles are just big enough to scatter light. You know when you see sunbeams cutting through a dusty room or a flashlight beam in the fog? That's the Tyndall effect. You don't see the beam in clean air because there's nothing to scatter the light. And get this, the reason the sky is blue? That's the Tyndall effect on a planetary scale. It's the ultimate visual proof that there are particles just hanging out up there. But the real secret weapon for stability is something called Brownian movement. It's just constant, non-stop motion. The colloidal particles are doing this crazy, random, zigzag dance. And why? Well, it's because the molecules of the medium, which are way, way smaller, are slamming into them from every direction all the time. It's like a game of microscopic pinball that never, ever ends. And here's why that matters so much. That constant chaotic dance is what keeps the particles from ever settling down. All that kinetic energy is actively fighting against the pull of gravity. The particles literally never get a moment's rest to sink. It's a huge piece of the puzzle for why colloids are so stable. But there's still one more secret to their stability, and this one is electric. There's this process called electrophoresis, and it shows something incredible. If you zap a colloid with an electric field, all the little suspended particles start moving towards the same side, either the positive side or the negative side. And what does that tell us? It proves they all have the exact same electrical charge. And what's the first rule of basic physics? Like charges repel. So, since every single one of those particles has the same charge, they're all constantly pushing each other away. They can't get close enough to clump together and form a bigger, heavier chunk that would sink. It's like a built-in force field. So let's put it all together. Think of a colloid like a crowded dance floor. The Brownian movement is everybody randomly bumping into each other, so no one can stand still and just leave the floor. And that shared electrical charge? That's like everyone having a personal bubble, so they can't get too close or form big groups. It's this amazing 1-2 punch of constant motion and repulsion that keeps the whole thing perfectly stable. So next time you see fog, or pour milk in your cereal, or even just glance up at the blue sky, you'll know what's really going on. You'll see that invisible science at work. Our world is just packed with these incredible mixtures, all held in this perfect, delicate balance. So now that you're in on the secret, go out there and see how many colloids you can spot today. I bet it's more than you think.